So you will see how proofs strongly relate to predicate logic. Okay. To do a mathematical proof, it consists on making a certain inference step. Okay, based on certain basic knowledge or definitions that you have in hand. Okay, so it's exactly the same. This is why it fits within this time slot in this course. So a proof is a valid argument that establishes the truth of a statement. Okay. And an argument, do you remember what's an argument? Okay, so it's just a set of inference steps. Okay. In math, computer science, and other disciplines, informal proofs, which are typically shorter than the proofs we use for inference, are generally used in this way. So you have more than one rule of inference applied on the go. Okay, so make shortcuts. You don't go into the details. You skip certain steps, and hence this is prone to error. So it's better actually when you have a very serious proof to do is to go step by step, okay? And to make sure that every step is justified, every argument is valid. You are only using valid predicate logic formulas. So, أكيد proof have many practical applications in the verification of computer programs, and the advancement in mathematics and physics and in basically all sciences. And just some terminology before starting with the core of the session. So a theorem, what is a theorem for you? That is proved to be true, okay? Yeah, when it's not proved to be true, then it's just a conjecture, okay? Once you prove it that it's true, then it becomes always true, okay? A lemma, it's a helping theorem that you can use in other theorems. So typically, they are previous results that can contribute to the proof of a certain bigger theorem, okay? The theorem has a certain hypothesis, like the declaration of a theorem has a certain hypothesis in it, and you have a certain conclusion in it. Yes. No, it's actually part of the property. It's just a different way to see the property. Okay, so or it's part of the truth that you have in the theorem. Okay, maybe a side effect of it. Okay, say you have, if you want to prove something about integers, then you can prove a certain property about odd integers, about even integers, and then these two lemmas can contribute to the proof of a certain generalized theorem about all integers. A corollary is a result which follows directly from a theorem. Once again, it's just a view of the truth that is in the theorem, and typically can be the lemma of another more advanced theorem. But when you are not sure of the truth of a certain property, then it's just a conjecture for the moment. Once a proof is found, then it becomes a theorem. Once someone discovered that there is a pitfall in the proof, then the theorem will be refuted once again, and maybe you will find that anyway it's useful because it's true in this and that case, but not in all the cases. Okay, but due to a very quick step done in the proof, they didn't pay attention to that property or to those special cases, and so on and so forth. So yes, this happens. Okay, even if we have very rigorous mechanisms for this. You mean if you find that a certain inference step is incorrect, okay? So usually after publishing a certain new proof, other mathematicians will study that proof, the proof itself, okay? And will check every single step in it, okay? And I will start thinking about all the possible cases, whether this is true or not, whether that definition has been misused here or there, okay? And just decorticating, like getting into the details. And then if they find a certain flaw in the proof, they would refute the original theorem, but most probably you will find that it applies for a big fragment of the study domain, okay? But only in those cases you have to refine to further tune your proof, okay? So just to tell you that this happens, but we don't give up. We don't stop doing proof. No, on the contrary, we have to keep doing them, okay? They have different forms, but so often you have this form. You have a universal quantification, something like this property that you are used to hear and read in mathematics. If x is greater than y, where x and y are positive real numbers, then x squared is strictly greater than y squared. I think you agree on this property. It must be true for every x, for every y. And what I just said, for every x, for every y, it's hidden in this sentence, okay? So where x and y are real, positive real numbers, means for every x and y being positive real numbers. So we can rephrase it as follows. For all positive real numbers, x and y, if the property x is strictly greater than y is true, okay, then necessarily the property x squared is strictly greater than y squared is true, okay? So to check the general case, we have to visualize theorems in this way. For every x, if you have a certain property of x, then necessarily q of x, okay? This whole implication, P of x implies q of x, can be called a certain R of x, okay? So for every x, R of x is true, okay? But it's much easier to you to see it as an implication. So even if you have a certain property, like, I don't know, like prime numbers are blah, blah, blah. It seems as a one single sentence, but try to analyze in this case the meaning of that description of the prime numbers, okay? Make it as an implication. So if a number is not divisible by because it's prime, then it has that property, okay? So try to formulate your theorems in form of an implication. You will see why, okay? They become much easier to either prove or refute, okay? So in this case, we want to prove that for an arbitrary C, P of C implies Q of C, okay? Good. So how to do this? Actually, by universal generalization, if you have P of C implies Q of C for every C, then you can generalize it for in the original form. For every x, P of x implies Q of x. So we must prove something of the form P implies a Q. Okay, if it is a prime number, then it has that property. Okay, for example. So you have different cases. We want to exclude the very easy one, the trivial and vacuous proofs. For example, for the trivial proofs, is when you have when you know that Q is true, is always true. Okay, so you can use whatever P to imply it. Okay, example: if n is even, then 1 is equal to 1. Okay, so such kind of theorems are not really useful at the first place, but just in case you're interested in such a property, then you can actually easily prove it, because Q is always true, no matter what P is. Another example that seems a bit more credible, for integers n, if n is the sum of two prime numbers, then either n is odd or n is even. Okay? So it seems appealing at the first sight to be proved or adopted as a theorem, but actually you don't even need to bother to prove it, because it's by default always true. Okay, and regardless of the premise, okay, of the hypothesis of your theorem. Okay, do you agree? So actually, pick up any number n, it's either odd or even. So, okay, regardless whether n is the sum of two prime numbers or not. Okay, so actually, a corollary of the fact that n is either odd or even is that numbers, okay, that are the sum of prime numbers are also either odd or even. Vacuous proofs are proofs where you have P always false, okay? So they are also obvious to prove. They are always true. For example, if n is even and odd at the same time, then we can prove that 2 plus 2 is equal to 5. Okay. So well, actually, you will see that, okay, so maybe with a directive proof, you can start from a certain imaginary number n being equal to certain 2k and to 2k plus 1 at the same time. And then you can reach the case where 2 plus 2 is equal to 5, okay? But you may also discover plenty of things that maybe 1 is equal to 0 in this case, okay? Because if you subtract 4 from 2 plus 2 and you subtract 4 from 5, then you get 1 is equal to 0. You will get plenty of false things being proved with you, just because you have a false premise to this, okay? So this is what I say so often in my discussions, daily life discussions, like if you make something wrong, if you accept something wrong, then you can, like, you will find yourself forced to accept anything else afterwards. If false is true for you, then anything else can be true, okay? If you accept contradictions, then you have to accept anything else, okay? So, well, such type of theorems, they are easy to prove, but they are typically useless. They do not bring up useful information. We are obviously interested in the other types of proofs, okay? And how to proceed with proofs. So you will see plenty of different ways. We will use direct proofs. We will use proofs by contradiction. We will then use backward proofs, okay? So we will start from the conclusion and try if we can find the required elements in the premises to prove the conclusion. We will use proof by case, okay? So for example, if we want to prove something for any integer, we try to prove it for even integers, for odd integers, and stuff like that, okay? If we are proving a property about the absolute value of certain numbers, then we check the case where those numbers are negative and the cases where they are positive. And if you are able to prove the property for all these cases, okay, then we would have proved the property for any real number, okay? So let's start with direct proofs. If you have to prove that for every x, when p of x is true, then q of x is true. So you start from p of x, and you try to use all the mathematical definitions and rules and regulations that you know to prove finally that q of x, okay? Example, if n is even, then n squared is also even. How can you proceed with this one? It's just good to do the same thing at home, to stop the slide at this line and to try to prove this on your own, okay? And then check your answer at the end, okay? So I'm gonna do it with OneNote. So we want to start from n is even, and we want to check that n squared must be necessarily true. N squared is even must be necessarily true. Okay, so let n be an even number. So we have to start from the premise, and then step by step we have to reach the conclusion. So usually you should be able to make certain progress. You must be able to analyze that property. So by checking its definition, by replacing n by something else, and so on and so forth. So what does it mean that n is even? So n typically, so this means that there exists actually a certain number k such that n is equal to 2 times k. Do you agree on this definition? Okay. Well, in this case, this means that n squared is equal to 2k squared, which is 4 times k squared. Okay. So this means that n squared is equal to 2 times 2k squared. Okay. Do you agree? So we can call this k prime, and then we have just shown that if n is an even number, then there must be a certain k prime. We know what is it, okay? We just calculated, we know, okay? We can pinpoint it. So there exists a certain k prime, particularly, actually, it's equal to 2k squared, okay? Where k is blah, 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 okay? such that n squared is equal to 2 times k prime. And this is the exact definition of even numbers. Okay, so now we can make we can restitute this into the definition of even numbers, and we can prove that n squared is even. Okay, good. Any question about this one? Okay, well, this one is quite easy, I admit. So let's check another case. If n is odd, then n squared is odd. Sorry? Yes. So let's replace n by 2k plus 1. Well, 2k plus 1 squared is equal to 4k squared plus 4k plus 1, which is 2 parentheses something plus 1 at the end. Okay, and this is the exact definition of an odd number. So n squared must necessarily be odd too. Okay, so I think you have the proof in the slides. Okay, so it's kind of like you can rewrite it as 2r plus 1, where r is equal to 2k squared plus 2k. Okay, good. Okay, sometimes you cannot use direct proofs. It's hard for you. So let's you have a third example about rational numbers. Okay. So the real number r is rational if there exist integers p and q where q is different than 0, such that r is equal to p over q. And we want to prove that the sum of two rational numbers is rational. Okay. So once again, it's straightforward. You just have to use your knowledge in mathematics, basic mathematics, to prove that finally this is equal to p times u plus q times t over q times u, so which is something like v over w, okay, where v and w are integers, okay, or so you could do the same for the sum of those two rational numbers, okay. So sometimes this is not easy to do direct proof, okay. In this case, you may proceed by contraposition, okay? It means that you prove that if not q is true, okay? So if q is false, then necessarily p is false, okay? As if you were proving that not q of x implies not p of x for every x, okay? This is exactly as similar to proving that p of x implies a q of x, okay? Example. Prove that if n is an integer and the 3n plus 2 is odd, then n must be necessarily odd. Okay, let me take this as a screenshot and let's do it together. Okay, so prove that if n is an integer and 3n plus 2 is odd, then n is odd. If you start with a direct proof, all that you can say about 3n plus 2 is that it is equal to some k plus 1, 2k plus 1. Okay, do you agree? But then in this case, if you want to isolate n because we want to prove that n is odd, then you get something very weird, something like 2k minus 1 over 3. And you have to proceed by case, okay, to check all the possible cases where this is divisible by 3 or not. And okay, so you cannot really conclude a big thing about n. I don't think that this is similar to having, you cannot rewrite it in form of a 2 times something plus 1, okay? Do you agree? Okay, so a direct proof here is not helpful. So let's try to prove it by contraposition. So what about proving this by contraposition? in this case, we have to consider the negation of this one and do a direct proof to reach the negation of that one. Okay? What does it mean? So we have to suppose that n is even. Okay? Suppose n is what? Is even, is not odd actually. Okay, so we start with the negation of the right-hand side of the implication. And then we should be able to prove finally that 3n plus 2 is what? Is not odd, which is even. Okay? Good. So this is our target. Let's check if we can do it. So suppose n is even. In this case, there exists a k such that n is equal to 2k. And in this case, 3n plus 2 would be equal to what? 6k plus 2, which is 2 times 3k plus 1. Okay, so it's 2 times something. Okay, and this is a valid proof. Okay, using our knowledge about logic. Okay, that contrapositions, contrapositives are 100% equivalent to original implications. Okay, and this is, guys, different than proving by contradiction. Okay, so maybe this is the only part that on which you may have a certain confusion, because sometimes during the exam you are asked to prove something with any way, with any process, any method you want, but you have to tell us which method you used. Okay, so just pay attention to the difference between proof by contrapositive, okay, by contraposition, and the proof by contradiction. We will talk about contradiction in a few slides. Is it fine for the, yes, please. Yes, this concludes the original proof. Okay, because when you're okay, so when 3n plus 2 is odd, n actually cannot be even, and it happens that if n is not even, then n is odd. Okay, so just because the dual of odd is even, when you put the negation, you get the other case. Yes, good. And now actually we can prove that n square, if n square is odd, then n is also odd. If you try to proceed with the usual way, replacing n squared by certain 2k plus 1, it's, yeah, you will have a certain radical when you calculate the value of n. Okay, so you don't have sufficient insight. How can you proceed very quickly with contraposition? So when n is even, then n squared is necessarily what? Even. Okay, we just proved this at the beginning. So now we have a proof for these two cases. Okay, good. Okay, the proof by contradiction is something different. Okay, the proof by contradiction is to prove that when you negate the implication, and the negation of an implication, not P or Q, P implies Q, it means not P or Q. Its negation is not, it's P and not Q. It's where the premise is true, yet the conclusion is still false. Okay, you have rain, but you don't have clouds. Okay, and but means and actually. Okay, so if the proof by contradiction is useful because sometimes part of the reality, okay, of the facts exists in the premise, and part of the mathematical properties exist in the conclusion. Okay, you cannot go from one to the other easily, not from the negation of the conclusion to the negation of the one, the first part, the premise, easily, neither with a direct proof. But simply if you put both of them together, then you have something that cries actually a contradiction, a conflict. Okay, they cannot be both at the same time. So you cannot have P and not Q at the same time. Okay, so in the premise you have certain facts, in the conclusion you have some other facts. If you put them together, then you will have a clash. You will have a contradiction. Okay, so when you do a proof by contradiction, you are actually proving that not P, okay, but here it's not P. So I have to clarify this. Um, so actually, just to clarify this point, because they are abusing they are using the symbol P to denote two different things. Okay, so if my theorem is called T of X, okay, so I have for every X T of X. If it happens that T of X is if this is equal actually to for every X P of X implies Q of X, okay, then a proof by contradiction is to show that we cannot have T of X, okay? Not T of X is actually is false, okay? And this is equivalent to proving that for every X, not P of X, sorry, P of X and not Q of X is false, okay? So what does it mean is false? Actually, it implies false, okay? And proving that this part here, okay, implies false, okay, which is T of X implies false. Well, this is by contra, actually not T of X implies false, by contrapositive implies this is equivalent to proving that T of X, sorry, that true actually, true implies T of X. And true is always true, okay? So true. So this means that T of X must be necessarily true all the time. Okay. So the proof by contradiction is to consider the negation of your theorem and to prove that it leads to false all the time. Okay. How could it lead to false? Just by having certain assumption on the fact that, let's say, X must be positive in this case. Okay. And then at the end of your proof, to reach a phase where X must be necessarily not positive, less than or equal to 0. If you have these two facts, then you have X is positive and not X is positive at the same time, and then you will have a conflict. Okay, so you have to start with the negation of your theorem. So I'm sorry, this is not clear here. So you have to start with not T of X, and to lead to a certain contradiction. How can you get false from your conclusions? Just by having a certain moment, certain fact A and not A. Okay, anything of this form. Okay, so X must be positive or Y, and somewhere else you see that X and Y cannot be positive in your proof. So you have A and not A at the same time, and then you have false. If you proved that not T of X, negating your, contradicting your theorem, leads you to false necessarily, to a contradiction, then this means that the true implies your theorem. Your theorem is always true. Okay, it cannot be false. Okay, yes. Um, Actually, if we have, like usually while having proofs, we didn't say this. When you have a certain property, such as the sum of the first n integers is equal to n times n plus 1 over 2, what we did at the first session. So we have this feeling, we have this, okay, but we were not sure whether it holds for even and odd numbers and so on and so forth. We could do proof by case to consider even and odd numbers. And we could also try to negate that property. So let's assume it's not true. And eventually we could get a certain contradiction in the proof, okay? In that way, we would have proceeded in this way. We would call it contradiction. Okay. So usually when you have a strong feeling about the truth of P implies a Q. Okay. But you're not able to do it with a direct proof, not by contraposition. Okay. Then try to put P of X and not a Q of X together. Okay. And try to conclude false from it. Try to check if you get a contradiction at the end, a false from it. Okay, if it is the case, then it means that P and not Q is always false, which means that it's either not P of X or Q of X, which is P implies a Q, which is your original theorem. Okay, let's do it with an example. Use the proof by contradiction to give a proof that square root of 2 is irrational. You know what's an irrational number. Okay, so well, to talk about all irrational numbers, okay, instead of talking about all irrational. So you can assume that square root of 2 is rational, okay, and then check whether this would lead to a certain contradiction, okay. Do you get the point? Okay, so instead of thinking about all the cases, because if you can calculate the square root of 2 and get its value, so maybe you can show us that it's irrational. But instead of doing this, okay, think about the possibility where square root of 2 is rational actually. Try it out and you will see that eventually this will lead to a certain contradiction at the end, okay? So suppose that square root of 2 is rational. This means that there are some certain a and b such that square root of 2 is equal to a over b, okay? And b, by the way, must be necessarily different than 0. This is a very definition of a rational number. Good. We also must have another property, which is a and b must have no common factors, okay? Once again, because it is a rational number. So, good. In this case, 2 would be equal to a squared over b squared. This makes a squared equal to 2b squared. And this means that b squared is even in this case. We will reach this final conclusion. Okay, but at least we are sure now that a squared is even. We have just proved that when a squared is even, necessarily a itself is even. So now we are using another theorem as a lemma in our theorem here. Okay. So we can rewrite b squared, because finding that a squared is or a is even is not it does not lead to contradiction yet. Okay. All the facts that we have and that we may contradict is the fact that square root of 2 is equal to a over b. B is different than 0. We have nothing that contradicts this until the moment, and that b and a have no common factors. They have no common factors. We cannot reduce a over b anymore. Okay. But if we replace a by 2k in this formula, then b squared would be equal to something like 4k squared, 4c squared. Okay? We can divide by 2 both parties, and then we get b squared must be necessarily equal to certain 2 times a certain other integer. And here comes the contradiction. Because if b squared is even, then b is also even. So a is some 2 times k, and b happens to be something like 2 times k prime. So they have common factor. Okay, so you see, finally, we get 2 different sentences in our logical sentences. One stating that a and b have no common factors. Here we have a and b, they have a common factor, which is 2 at least. Okay. So we have a contradiction in this case. So when we negated our original property, which is square root of 2 is irrational, we supposed that it is rational. This has led to a contradiction at the end, has led to two different conflictual facts. So it cannot be the case if square root of 2 is rational implies false, okay, then necessarily true implies square root of 2 is irrational. This is why square root of 2 is irrational. Okay, good. Is it fine? So students, I know that at this moment things get like a bit serious, because maybe you are wondering right now, oh, I wouldn't have thought about this proof myself, okay? And due to time reasons, I have to make a choice, so we cannot spend a lot of time trying this out, okay? But now, guys, you are able to prove that square root of 3 is irrational. You have the tools, okay, and the set of ideas, okay, to help you to think out of the box and to prove similar problems, at least, okay? And it never ends, okay? It never ends. In mathematics, making proof, it's one of the hardest tasks, okay? So it's completely fine. But so usually during the exams or quizzes, you will have something quite similar to either what we have discussed in class or on the slides or with the exercises, okay? So once again, you will find that maybe a relatively difficult set of exercises in the assignment. Okay, but the goal is to get you trained on this palette of possible proof methods, and so that you can do better on the exams. Yes, question. Usually, you will see once again, the scope is what we covered, slides, union, practice exercises, okay? So I think if you are able to solve all of those exercises on your own, okay, and to get correct results at the end, they are sufficient, okay? But of course, if we ask you a certain property about geometry, then you have to review your seventh grade geometry book, okay, maybe, I don't know, okay? So we don't make a lot of assumptions on what you know or not in mathematics, okay? So you will see they talk about very basic properties, okay? Yes. For what? Mm. Uh, no, it's not mandatory. So as long as you can do it with Word, it's fine. Okay. So as long as you can do it with Word, it's fine. It's not a big deal. Yes. Okay. Um, when you have a bidirectional statement in your theorem, I think you know already what to do. You have a double implication. So you have to prove what? Both directions. So you have to prove that P implies a Q and that Q implies P. And maybe from P to entail Q, it's okay to do a direct proof sometimes, but to prove that Q implies P, then you have to proceed by positive, okay, by contraposition. Or maybe you need to do a proof by case, or maybe you have to proceed with a proof by contradiction to put P and the Q, and then you get a contradiction, okay? So, sorry, a Q and not P, and to conclude a, okay? So each direction can be proved with a different method. It's up to you, okay? But you will see that they do not cover the exact cases. P implies a Q has a completely different meaning from Q implies P. So each direction could have a different difficulty level to be proved, and you may use different methods to prove each direction. That's all that we want to say. So for example, to prove that if n is odd, then n square, n is odd is true if and only if n square is odd. Well, we do it actually, but we did it, but we did it in two different ways. We proved from n odd to n squared is odd, we did it with a direct proof. The other way around, we proved that when n squared is not odd, then n is not odd neither. Okay, good. Another two type of proofs is the constructive existence proof. So sometimes your theorem is just about the existence of a certain instance. Okay, for example, show that there is a positive integer. Show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. Okay, so you have to find a certain number such that you can write it as a cubed plus b cubed and as d cubed plus c cubed. Okay. Well, in this case, you have to find that number. Okay. Maybe you have a certain more generic property, a certain universal theorem that relates to it. So you know that that property applies to all the numbers having a certain property, and then you can directly catch up one of them. Okay. Or simply you haven't studied that domain that much, okay, so far, and you have to make it with trial and error. And this is actually what scientists have done for this proof, for example, okay? They continued trying out certain numbers until they found this number, 1729, and it happens to be writable in terms of 10 cube plus 9 cube or 12 cube plus 1 cube. and it has been discovered by those scientists. So actually, you can you have a funnier story about this in the book. You can read it on your own. So in this case, computers would help in finding those instances. Okay, so they can do the silly work. They can try out all the possible combinations, because while picking up the A, B, C, and D numbers, okay, they are necessarily less than or equal to the original number. Okay, so this is why it's an algorithm that terminates. Actually, eventually you can find it. So if you pick up any number n, it's useless to try anything beyond n. You can try all the lower numbers and try all the possible combinations. It takes a lot of time, but you can do it. Okay. And just one last word about this. So usually when we have certain properties like this, okay, we start checking the instances, okay, and then analyzing those instances that check if there is any relation, if there is any pattern that repeats in them. And most probably after the proof of this existence, you can generalize this into a universal quantification about that property. Any number that is, I don't know what, prime and has mount type can be written in that or this way. So this is how they usually proceed in mathematics. Non-constructive existence proof is actually a bit harder, maybe. So you have to assume that no C exists, which makes P of C true. So now we get back to the original format. We want to prove that for every X, it's not the case that P of X. Okay, so show that there exists irrational numbers X and Y such that X to the power of Y is rational. Okay. So what we can do, sorry, we can show that there are irrational numbers such that X to the power of Y is rational. Okay. Well, in this case, we can, yeah, instead of finding them, because you have very large domain, checking all the instances sometimes. Okay. I think yes. Okay, finding one instance is good. Okay, it's a sufficient proof because it's yeah, you proved it. Okay, but sometimes it's very hard to find that instance, that example. Okay, so in this way you can proceed in a non-constructive existence proof, where, for example, you assume that there is no C such that P of C. Okay, and then you prove that you get a contradiction at the end. Okay. So in this example, for instance, we can say that we cannot find any two irrational numbers, x and y, such that x to the power of y is rational. Okay. This means that if you pick up any two irrational numbers, x to the power of y is what? Is irrational too. Okay. So now you have a nicer property that you can use to contradict, to make a contradiction at the end. Okay. So once again, you have to pick up certain instances to make your contradiction. So you know that, for instance, square root of 2 is irrational. Okay. Good. In this case, square root of 2 to the power square root of 2 must be irrational according to your new assumption. Okay. Good, because if you consider x to be square root of 2 and y to be equal to x, then x to the power of y, which is square root of 2 to the power square root of 2, is irrational. Good. Now you have this number being irrational. If you consider once again that square root of 2 is irrational, then x to the power of y, okay, square root of 2 to the power square root of 2 to the power square root of 2 must be irrational. Nevertheless, if you do a tiny calculation, this is actually square root of 2 to the power square root of 2 times square root of 2, which is 2. And this is equal to square root of 2 square. which is simply 2. And 2 is not, it is rational. So in this case, you would have shown that that your original assumption was incorrect. Okay, so you can find finally certain instances. Okay, so it depends on your property once again. Sometimes it's easier to proceed directly with the existential constructive existential proof or with the non-constructive existential proof. Sometimes you have a property that says something about all the elements, okay, and you want to contradict it, okay. In this case, it's sufficient to give a counterexample, okay. So if you're asked to prove that it's not the case that all integers are positive, let's say, okay. So, well, you know about the existence of 0, which is not positive, okay, and vice versa. So you can use also a proof for a contradiction on the for every x p of x to show that there exists an x with not that property, even if you don't know which one exactly. Good. So this is called a proof by counterexample. So once again, guys, you have to distinguish between contraposition, contradiction, constructive existential proof, and counterexample. You have C in all of them, okay, and contra something, okay, but they mean different things. Counterexample is to refute a certain universal quantification. It's not true that all the integers have that property, and here is one, okay. With constructive existential proofs, it's the same. I'm proving that there exists an x such that p of x, okay. Maybe the aim with counterexample is to refute a universal quantification, to show that there exists an x such that not p of x, okay. In this case, I can prove not for every x p of x. Contraposition and contradiction, we already discussed them. Good. You have to be very careful when you draw out conclusions with proofs. So let's check this tiny pitfall in the proof here. We want to prove that 1 is equal to 2. Okay, so we consider this as a proof. We consider two numbers that are equal, a and b. In this case, a squared is equal to a times b. Do you agree? In this case, a squared minus b squared is equal to a times b minus b squared. Completely fair to say this. Step number 4, this means that a minus b times a plus b is equal to b times a minus b. It's completely fair. Step number 5, you get a plus b equal to b. Okay. So the problem is here at this phase. Okay. If you do this very sloppy step, then you can reach to b equal to b, which is 2 is equal to 1. But if you pay attention, then you discover that you cannot do it. Okay. So you know all these social media posts and okay, so about simplifications that you can do. So just pay attention to this. Why do we do this usually? We completely understand the students who do it because they are driven, they are frustrated, they want to prove something, they use certain shortcuts. So we are just saying, like, don't be fooled by such steps, okay? Good. The summary here is if direct proof do not work, then in this case, we may need a clever way to prove the same concept or theorem by contraposition, or we can proceed by contradiction. We put P and not Q, and we lead to a certain contradiction to false, or we show that the theorem does not hold using a counter example. Okay, because sometimes the theorem itself could be false. So in certain type of exercises, which are the real life exercises that you are faced with, the question is as follows. So prove the following theorem, okay, or simply refute it, okay? So prove or disapprove that property. And here the possibilities are left, are so many, and the problem is left to you. Good. There is one particular type of proof, which is proof by induction. We will review it in multiple sessions later on, okay? But the next step is to, after the break, we will get 10 minutes break, and then we will resume for 50 minutes about the last part about the proofs. We will see proof by case and the backward proof, okay? The two main remaining types of proofs. Thank you. Yes بس حوقف التسجيل and then